I'm Sumanth Prabhu. I am at Washington University in St. Louis, and I'm the chair of the BCVS Specialty Conference Committee.
I'm Farah Sheikh. I'm from the University of California, San Diego, and I'm currently vice chair of the BCVS Specialty Conference.
And we are here, both of us, with Dr. Dale Able, who is the William S. Adams Chair and Chair of the Department of Medicine at the David Geffen and UCLA School of Medicine. And he was our 2024 BCVS Keynote Lecturer. And this is a behind-the-scenes conversation that we're going to have with Dr. Abel to find out what makes him tick, and also what drives him in the scientific world and beyond the scientific world. So, Dale, welcome. Thank you for being our keynote lecturer.
Well, thank you very much. It's a real honor and privilege to serve as your keynote lecturer this year. I actually didn't expect to get a plaque, so that actually makes it even that much more special. And so, you know, it's a real privilege to be recognized in this way for the work that we have done to contribute to cardiovascular science.
Sure, thank you. Maybe I'll start off. First of all, it was a very impressive lecture. What struck me was just the breadth and depth of your work in the area of cardiac metabolism in general. This raises in my mind, how do you settle on your scientific questions? How do you develop your hypotheses? And obviously it's where the data leads you, but how when you start out, how do you think of things? So.
Yeah, that's a very good question. So I'll just probably give a little bit of background because in one sense, you know, I'm an endocrinologist, I'm not a cardiologist. And so it's like, well, why am I in this tribe, right? and so, you know, my journey in this area started off with, you know, a simple observation that if a heart didn't use glucose, it's hypertrophy. And so then the question was, you know, what did this have to do with anything? And it turned out roughly at the time that diabetic hearts didn't use much glucose and that they tended to hypertrophy. So to answer your question specifically, the way that I go about generating a hypothesis is if I see two dots that need to be connected, then the question is, how might these dots be connected? And then the hypothesis really is that I hypothesize that the connection between these two dots is some maybe third dot, and then go ahead and test that. So that's the general approach that I take to scientific inquiry in general. But this, afterwards, you kind of follow the data, because even as I was discussing with the trainees who came to lunch today, what I think makes science fun and creative is when something actually doesn't add up. And you've repeated it 3 times and it still doesn't add up. And then you say, okay, there's a reason why it's not adding up. And therefore, that's what then forms the pivot to a direction that sometimes you're lucky and it comes out to be something really important.
I want to follow up a little bit about the early careers. You know, for those starting out in the cardiometabolic field, where do you think that they should sort of put their eggs in the basket? And I know you had a lot of great basically ideas at the end: fix the leak, don't think about ATP only. But if they wanted to start in this field, where do you think the new trends are moving towards?
Yeah, it's a very interesting question. So the way I like to think about this, rather than think as like, you know, where is the new trend? Because remember, every trainee has something that they're good at, right? And so if you're trained in, let's pick something, you know, worm genetics or something, right? But you feel you want to study cardiometabolic disease, then you ask yourself, you know, what am I good at? And what expertise do I have that I can then potentially apply this to a question? So I would always start with the skill set and the training, and then ask, what are the big questions in the field? And, you know, I think the way that one goes about that is to get a sense of, you know, what are people studying? Everybody's talking about HFpEF, for example, and I will tell you my personal bias is that I think HFpEF is a systemic disorder where the heart is maladapting to a metabolic milieu which is abnormal and probably linked in some to a certain extent to many of the traits that we would put in this big bucket called, you know, cardiometabolic. So in my mind, some of the questions are, you know, what are the systemic signals that the heart maladapts to? I think that's I think it's still an open question. Second, you know, if the heart is maladapting, then how can we detect it? And then thirdly, how can we fix it, right? Because it is possible that you might try to fix the end organ and it's actually the water supply, right? That is the cause of the problem. But in one sense, it doesn't really matter, because if you fix the end organ and it still doesn't fix it, then you've learned something, right? And then you ultimately move on. So if someone is coming into this area now, and it's obviously a very hot area, it's expanding, it's, you know, everybody's going to be doing this. Not everybody, but a lot of people are going to be doing this for a long time. I would say talk to leaders in the field, read what they're writing, ask yourself, okay, this is a really interesting paper, but you know, I think that their conclusion might be overstated. I think that there are still 3 or 4 or 5 remaining questions that this needs to address, and then you decide whether or not your skill set or your tools or your environment could actually allow you to begin to pursue those questions.
You're an endocrinologist, but I think of you as an honorary cardiologist.
Thank you,
So
sir.
let's just put that
Yes.
out there
Right.
first. I wanted to get back to this your scientific approach for a minute. So, at least in my career, things are nonlinear in how you decide, you know, something might be to what something actually is. So, I'd like to ask you, what was your most surprising scientific discovery? That's the first part. And
Okay.
which discovery are you most proud of throughout your long career?
Those are very difficult questions, because I think I've had many surprises, to be honest. I think that some of our most exciting observations have been the ones which were, you know, least expected. But I was saying to the trainees earlier that, you know, we write our papers like we're really smart. Like we knew all along that we were going to solve this, and this is exactly how we're going to solve it. And the answer is that that is not the case. So I can give you a number of examples. I'll start with some, you know, very early work that we did with regards to the insulin receptor and its signaling on the heart. And you know, I came off, I guess, into my scientific independence at the time when people were, you know, knocking out genes in mice in a tissue-specific way, and so that was the thing to do. And you know, I got into the insulin receptor kind of by accident, because although my lab was a glucose transport lab, just across the street at the Jocelyn was an insulin receptor lab, and they were knocking out of everything, but they didn't know about the heart. And I said, okay, can I have that, right? and so we did that, and the first thing was the hearts are small, and insulin is not, was at the time wasn't really believed to be a growth factor. I mean, it's all about metabolism. But IGF-1 was a growth factor, but we not with IGF-1, those hearts were normal in size. So that was the first like thing that this is kind of interesting. And then when we began to dig a little bit further, we actually saw that insulin signaling itself had a very important trophic effect, not only just on you know, the muscle, but also on the mitochondria. And people think I'm a mitochondrial expert. I'm not. I mean, I didn't know anything about this, but I had a postdoc who came and I said, look, you know, we have this animal, it has a little heart, and when we perfuse it, it has high glycolysis and low glucose oxidation. And she looked at me and says, it's the mitochondria. And I said, okay, come to my lab, because she has a background in that, and said, let's, and in fact, she was right. You know, and so I would say that that little aberration, or just what I was describing as a phenotype, really unlocked an understanding of how critical mitochondria were to a lot of the cardiac adaptations or maladaptations to the cardiometabolic states. I can know, you know, masquerade as a mitochondrial expert, right? But it really was this initial observation that then drove us, you know, in that direction. And now every new project that we have in the lab, it's, I don't know what to expect, right? You do it, you go for it, and then it's like, oh, that's a really interesting observation. And what I always, you know, say to the folks in the lab is like, don't come knock on my door until we can have a discussion as to why, right? And so, you know, I always really force those who train in my lab to try to get to the why. It's one thing just to describe it, and it's like, but then it's like, why? And that, I think, has defined the work that we have done.
You know, you're an amazing mentor to many, and I think about how were you mentored and who were your mentors? Can you speak a little bit to that?
Yeah, so I've had many mentors over the years, some terrific, some not so terrific, and nobody will be named on this publicly available video. But I would say this, that the one thing that has really stuck with me across the years is the generosity of mentors, right? Because I think one of the hallmarks of mentorship, which I have internalized, is when people actually just take the time to actually listen and try to understand, how are you thinking, how are you feeling about the experiment, as opposed to tell you, here's what you need to do. It's actually, what do you think about this? And so one of my early mentors, two early ones actually, um, there's one very early mentor who actually was a person who, my reaction to that person, I should say, drove me into diabetes and metabolism, was that he was so smart, and this was from medical school. He knew a lot about diabetes and metabolism. He wanted to make sure that you knew that he knew a lot about metabolism, right? And so I said, okay, I'm sure he doesn't know everything, right?
Yeah.
And so that was a push. But then when I went up to Oxford, it was like a little bit of the opposite. That my PhD mentor was just incredibly laid back, and he says, okay, he said, so I think you want to study something about metabolism. Well, I have a colleague down the hall who, and this is back in the day when this whole concept of insulin resistance and the metabolic syndrome was just starting to be realized. It's back in the 80s. And he says, okay, we think there's something called the metabolic syndrome, and it clusters with hypertension and these various things. We don't know why, but he doesn't know why, but he's looking for somebody who can help to think about this and maybe figure something out. That was it, right? And I said, okay. And then we talked, and we said, okay, if you're going to try to figure this out, what would you want to do? And these were human physiologists, and said, okay, let's find some people with hypertension who didn't yet have diabetes, and let's look to actually see if we can measure things in them that are consistent with cardiometabolic, what we now know, markers of insulin resistance. And that was it. And then we kind of went off, right? And it turns out that, yeah, that was probably true. But I had no idea a priori going to this, what I would have found. But at least it was like, when a good mentor will crack a door open, and you see like a little sliver of light, and you say, okay, I think there's light around the corner. I'm gonna go for it. And if all of a sudden the light bulb goes off, please leave a little cord, to the door, right, so that I can come back and find my way back. So I would say that those have been traits of mentors that I've personally enjoyed. And so when I mentor now, I also try to give people the freedom to explore, but to let them know that I'm not too far away. But I don't want them to feel like they're being smothered, right? I want them to actually go and shin their knee,
Yes.
right? Because that's then how I think they will then begin to sort of think beyond what they think they can do, and then actually become that much more creative.
So you're obviously a very successful scientist, but you're also a department chair.
Yes,
And
I am.
so beyond the personal one-to-one mentoring and advice you give trainees, we also know there are structural issues that are sometimes a challenge to developing the pipeline for future scientists. And as you know, physician scientists are also a endangered
Sure.
species. So I wanted you to maybe, as your experience perhaps as a chair, also as a senior scientist, what are your thoughts on how we can make the pipeline more robust, and how can we encourage more clinicians to pursue careers in science? And
yeah. So I mean, there are multiple layers to this question. So I would argue if you take a good chunk of students when they're medical students, and you ask them, do you think you'd like to do research? A lot of them are gonna say yes. And then they go on the wards, and then they see their attendings run around, clicking every box on the EMR, and trying to get patients out the door, and you say, oh, maybe I need to become good at that, right? And then you look around and you see that there are different kind of lifestyle considerations and so on, and so I think that one of the early keys is to actually let the students realize that it's the the career paths are very diverse. Is One isn't right, one is not right, and let's at least put in front of our trainees, opportunities to allow themselves to actually pursue something that they're truly curious about. So that's one thing, and I think that's like at the level of the medical school. I think many medical school curriculum are trying to build some of that into the curriculum where people can actually explore. I think the other part then is to create environments where the trainees are not siloed away from individuals who are doing science. And I think you know what I mean by that, right? So in many sort of academic medical centers now, the attending physicians for the trainees, it's like the residents, are hospitalists. So they are very good at getting people admitted, worked up, treated, and discharged. And that's what you're seeing. Of course, the consultants come in every now and again, right? But that's what you're seeing. And it's relatively unlikely you can have a physician scientist come around with you anymore these days. But which is actually rare in many places. And so therefore, creating an environment where the science and the discovery is valued is important. So one of the things I've done in both of the departments I've led at Iowa as well as at UCLA is to talk very openly about discovery and innovation and science, right? We talk about it when we're recruiting trainees. We talk about it. I have a weekly blog that I put out, and there's always something in there about somebody getting a grant, or somebody publishing a big paper, or somebody making a discovery, or somebody even having a post at a meeting, right? And so people see that, right? And so they actually recognize that this is actually part of being, I would say, a physician, not even necessarily a physician scientist, right? And so it's creating an environment where that is valued, but also where you remove the silos, because there's the clinical silo and there's the research silo. And when I talk to the clinicians, they actually tell me, yeah, why am I at UCLA or wherever? Because I want to be in an environment where discovery is happening. How can you actually give us more opportunities to have some of these conversations? So I think that's part of the environment. Now, of course, the headwind is, as you know, is medical economics, right? Hospitals run on razor-thin margins or negative margins, depending on the scenario. And so there are all these mouths to feed. And unfortunately, I think that a lot of the leadership in academic medicine no longer are physician scientists and are really focused on the business of medicine. And I get it. You need to have a robust business that will generate a margin to support. But then the fight starts when the margin comes, and it's like, oh, right, we need a new tower. We need, the MRIs are 5 years out of date. And
Where's
before
the research investment?
Exactly, right? And so, one of my brilliant obligation as the department chair is, if I don't fight for and advocate for the resources to support the research mission, there's probably very few others who will. Maybe the dean might, maybe the dean might not, depending on how the place is structured, because sometimes the dean is focused on the health system, right? And so on. So I think that really is just one example. And the actual percentage of the revenue that flows through these large, what I call medical industrial complexes, to actually sustain the research is single digit for all of the expenses to run the operations, right? But you have to make the case.
Right.
And then you have to, and it's not always an easy case to make, because a percent margin is a percent margin. And if somebody says, well, if I give that percent to research, then I have no margin, you still have to make the case, because ultimately our patients deserve it, right? Our patients deserve to be coming to a place where the people treating them are on the cutting edge of the field. Because we know this, we were all in very prestigious academic medical centers. We see referrals coming in, and it's like, how did that happen? Right? And so, I think we owe it to the patients who come to us, and we need to to inform those who are, making the business decisions why it's actually imperative for us to ensure that we can continue that investment, because that's then how we actually ensure that we maintain the quality that we believe we have, which we do for the most part. But I think that becomes really really central to that.
If I was to ask a question, I mean, I think it would be about the early careers. And if you were to think back to your early younger self, would there be any advice that you would give yourself, knowing what you know now about, the hurdles and all of the things that you've had to go through to get to this point?
Yeah, I mean, I think the advice that I think I would give, and I may have given it, is don't give up. I mean, there are many times early on in some of our early projects where it was like, I've tried this 15 times. It is not working. Right? And somebody's on the show said, so do it one more time, right? And so I would say that the one lesson that, and I would obviously convey to anybody coming now, is that very few things in life are guaranteed. I think there is maybe a generational sense. That's just, we're aging ourselves now. There's a generational sense that things maybe should be a little bit more predictable. And if I can't get to certain milestones within 2 or 3 tries, I should walk away and try something else. And I think it's encouraging those who are coming up to recognize the importance of persistence. And what helps that a lot, though, and I think what you're doing certainly with the early careers here, through the HN in the BCVS, is creating these peer networks where you get people at similar career stages just together and hanging out with each other, and actually realizing that you aren't rowing in that boat alone. And there's real strength in that. And some of the I would say some of my most seminal early experiences were in fact having peers who were having similar struggles. And then you actually realize that you weren't doing it alone. So that, you fell together, but you cannot celebrate together, because inevitably there's a win. And if it's your win, then I'm happy for you. If it's my win, you're happy for me, right? And so I think that is something which helped me early on, and which I would definitely want to communicate to those who are emerging, that perhaps the most damaging thing is to be in a place where you're feeling isolated.
Yeah. Maybe I could ask something on the lighter side.
Sure.
So most scientists that I've met that are successful and have a creative side outside of the scientific world or even the clinical world. Can you tell us what that might be for you?
What it might have been and what it was. So when I was much younger, I actually wrote poetry. Right.
Okay.
So that was a creative outlet. What I like to do now is I like photography. I like sort of landscape photography, and I like to travel. And so I like to go to places where I can see vistas and novel angles and pieces of architecture.
I think we've seen some of that on Twitter.
You've probably seen some of that on Twitter, exactly. And you haven't seen half of it. I mean, I can spend my whole day putting up pictures, which I haven't. But like you wake up and say, my gosh, this is an amazing sunrise. And so the first thing I do is I grab my phone. Which is like my camera these days, right? And I say, let me capture this, because I may not necessarily see it again like that, right? And so, yeah, that's an important.
So just like science, life is about imaging.
So as a true non-invasive cardiologist, but that is an outlet, and we definitely, my wife and I, we definitely enjoy going to just different places on the planet and interacting with this a broad diversity of people. And we find it very, very invigorating.
So I thank you for such an enlightening and
Thank you.
Enjoyable discussion. We, again, our appreciation for serving as the BCVS 2024 Keynote Lecturer. To everybody listening, I hope you enjoyed our conversation, and thank you for visiting.
Well, thank you.